We just saw that there is no added computational power to string together multiple linear transformations. A little disappointing, maybe not entirely surprising. But what we're going to see now is that there is added computational power by introducing nonlinearities and multiple linear transformations as well. So let me remind you where we are. We have our inputs over here, my 1, my x1, my x2. We're going to use this for XOR, which is why I have only 2 inputs. We have a multiple sets of weights. So the inputs will go through the superscript here, W1, W1, W1 is one set of weights. And then the the subscripts are going to tell us which set of weights. So 2, 2, 2, and then 1, 1, 1 are going to tell us what the weights are. And then we're going to sum them up and then apply a nonlinearity. And the nonlinearity we're going to apply here is that rectified linear nonlinearity, where what we do is we take the max of 0 and y. What does that mean? It means anything that's negative gets slammed to 0, and anything that's positive retains its value. So that was that hockey stick nonlinearity. Okay? Why did I pick that? You'll see in a little bit why. So out of this is not just the linear combination, but it's a linear combination put through that nonlinearity, and then we put it through another combination of weights with no nonlinearity. So the only nonlinearities are here. So the only difference between this network and the previous network is the introduction of a nonlinearity and these 2 internal neurons. Okay? So this again is the algebra that describes this neural network. I've got my input x1, x2. I've got these 2 constant terms that correspond to that. I've got these 4 weights that correspond to this over here. And then out here is W1, W2, which correspond to these 2. And finally, that constant term, which corresponds to this right here. All right, let's see what this simple change of a nonlinearity does to our XOR problem. Let me remind you what XOR is. I would like to output here a 0 when the 2 inputs, x1 and x2, are both 0 or both 1, and I want to output a 1 otherwise. Okay, so, well, let's see what happens. Now, what we really should do is sort of train this network, go through the update rule with this nonlinearity. I'm not going to do that. I'm going to tell you what the weights are for now, because but the purpose of this is not to train the network, but is to show you the power of these nonlinearities. So let's consider the following weights. 1, minus 2, unit value here, nothing complicated, 0, negative 1, and a 0 over here. Okay, so where do those weights come from? Let's not worry about that right now. But and by the way, there's the nonlinearity right there, F. So let's see what happens to our XOR now that we have it. So what do we have to do? We just need to put in 0, 0, 1, 1, 0, 1, 1, 0 into these values and see what the output is. And if everything works, we get one value when the values are the same and another value when they're different. All right, let's find out what happens. So let's put in 0, 0 and work through the matrix algebra. So this matrix times 0, 0, of course, is 0, 0. 0, 0 plus 0, negative 1 is 0, negative 1. Okay, what happens when we apply the pointwise nonlinearity to 0, negative 1? Well, the 0 stays at 0 and the negative 1 goes to 0 because we're clamping everything down. So I get a 0, 0 vector. I take a dot product with 1, negative 2, and I get a 0. Oh, good. 0 went to 0. That's what we wanted. Excellent. Good. Let's do 1, 0 now. All right, let's do the matrix multiplication. This row times this column is 1, and this row times this column is 1. So I get the vector 1, 1. 1, 1 plus 0, negative 1 is 1, 0. Apply the nonlinearity, nothing happens. 1, 0 stays 1, 0. Take a dot product with this, what do you get? The 1 hits the 1, the negative 2 hits the 0. Good, I get a 1. Excellent. So now I've got the right output for 0, 0 and for 1, 0. Let's do 0, 1. This is going to be exactly the same. 1, 1 multiplies this, I get a 1. 1, 1 multiplies this, I get a 1. Now everything is exactly the same, so I get a 1 in the output. The order of this doesn't matter because the rows on this matrix don't matter. Good, 3 out of 4. One more to do, 1, 1. All right, this row times this gives me what? 1 times 1 plus 1 times 1, 2. And then, of course, the next row is the same. So I've got 2, 2 here. 2, 2 plus 0, 1 is 2, 1. What happens to the nonlinearity to that? Nothing. 2, 1 stays the vector 2, 1. And now take a dot product with 1, negative 2. The 1 hits the 2, the negative 2 hits the 1. I sum them up, I get a 0. Wow, that's amazing. All I had to do was take the output of this linear system, apply this very simple nonlinearity that just zeroes out negative values, and I have solved XOR. And how did I do it? It's actually not really that magical. Essentially what I did is take those 4 values that I just enumerated, 0, 0, 1, 1, 0, 1, 1, 0, apply the nonlinearity to it, and what you will notice is that it shifted where these things live. So this the value here and the value here got pushed down, the 0 stayed up, and I essentially made my space linearly separable. That's the power of the nonlinearity. Linear transforms can't fundamentally change the space. What can they do? They can scale them, they can rotate them, and they can, for example, shear them. But they can't fundamentally alter the nature of the space. But the nonlinearities can. And what this nonlinearity did is essentially converted an otherwise non-linearly separable problem into a linearly separable problem. And that's sort of the magic of these simple nonlinearities. And that's the same reason why these nonlinearities work in support vector machines, is because they change the input space from something that is not separable to something that is separable. And then once it's separable, well, then the linear models take over. And notice in solving that XOR, I did actually have to do 2 things. I had to add the nonlinearity, but I also needed those added computations of multiple neurons doing different linear combinations. Okay? So that is the sort of neural net 101, if you will. Basic idea is very simple. We have linear models, we're going to add a nonlinearity, and then we're going to start wiring these calculations up in terms of multiple combinations of the input, and then multiple layers to keep doing more and more calculations. And the magic, of course, is that inside of those neurons are nonlinearities that convert what would otherwise be a very complex problem into something that is more manageable. And when we come back, we're going to see how to add even more complexities to these neural networks in terms of more neurons and more layers. And then, of course, we have to ask, well, what happens to the optimization? We showed you a little bit on how to do the optimization in terms of this iterative least squares or gradient descent, and we'll put all those pieces together when we come back.